Okay, so we're moving into chapter 15 in your textbook, which is called Electric Energy and Circuits. And it's actually the end, like the last section of the course, too. And we're going to start by right where we left off. We're going to start with the electric potential difference. In other words, with voltage. Okay? And if you remember, we did some questions where we talked about if you had a point here of some voltage and a point here of some other voltage, and this end was the end on the right was higher voltage, then we would need to do work on a charge to move it from the left-hand end to the right-hand end. The work, we would need to do work. And that work, of course, was equal to the change in the electric potential energy. And we were moving some charge Q, and so as a result, we got a change in potential. So whatever the voltage was on this side, it became something different as a result of the work that we did. Or if we knew what the change was, we could figure out how much work we needed to do. So the equation is delta V is equal to delta EQ over Q. Now in this unit, you will often see it written as W over Q. So instead of talking about the change in the electric potential energy, they'll just talk about the work done to move the charge. And lots of times the charge is at a potential of 0. And if the charge is at a potential of 0, then the delta V just becomes V, which would is what this side would be. Okay, so I'm just saying all that so that you don't get confused as to why there's not a delta. Okay, so the W is really the change in electric potential energy, and when the delta V becomes a V, it means we're starting with the V initial to be 0, because remember delta V is equal to VF minus VI. And so if the initial is 0, the delta V is equal to VF, and then we don't often put in the F because we're asking, like, so what is this voltage over here as a result of the work done? Now, back when we were trying to figure out, so working on electrostatics and stationary charge building up on an object, and it's kind of what happens with you when you scuff your feet across the carpet on a floor and then you reach for the doorknob. So charge is built up on you and the doorknob is neutral. And so when you reach for the doorknob, the charge wants to balance out, right? Two objects with different charges will share their electrons until they balance out. And the bigger the difference in the charge, the quicker, the more violent that sharing will be. And that's really what a shock is, right? A shock is an attempt of one object to really ground the other object, to take that excess charge off. But all of the charge that we've been looking at to this point has been that electrostatic charge building up on a surface or an object. So around the turn of the century, 17 into 18, so I think maybe 1799, there was an Italian physicist named Alexandre Volta. And he's the guy that gets credited for the battery. So what he did was he took layers of zinc metal and silver metal, and he stacked them, and he put wet paper towel in between them. Okay, so let's make this bottom one zinc, silver, zinc, silver. Okay, and he put wet paper towel between them so that would be like a conductor as well. And what he found was there was charge that built up on either end. On the zinc end, the charge was negative, and on the silver end, the charge was positive. And what he realized was if he connected a conductor, right, a wire, if he used a wire and connected the two ends, he could get a charge to flow. And then if he put some object in here, I don't really know what it would have been back in 1800, but that's supposed to be a really poorly drawn light bulb. He could make that object light up he was creating the first circuit. Okay? So what we now know is if you have one zinc and one silver, that will be a cell. And then when you stack more cells on top of each other, you get a battery. And they're really technically a volta cell and a volta pile, which we now call a battery. So our symbol in our circuits for a cell is a long line and a short line. And then if it's a battery, it's a whole set of them together. Okay? The short side is always, 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 always the negative side. And the long side is always, always, always the positive. So when you see this symbol for a battery, and it doesn't matter if it won't be a box around it. I probably shouldn't have done that because I would have just confused you. It doesn't matter if it has 2, 3, 4 sets. Usually how many sets mine have depend on how close it is to the bell ringing. The short side is always the negative. The long side is always the positive. The way I tell people to remember is the negative sign is pretty tiny, just like the short side. And if you took the positive sign apart and put it end to end, you would get the long side. Okay? Now, back when Volta was around, 1800 and thereabouts, they didn't actually know what positives and negatives were, and they didn't actually understand like where they were in the atom. We didn't figure out the structure of the atom until like 1910 to 1930. The discovery of the electron was 1909. Rutherford's model of the atom came around 1914. And so this is like 100 years before, 100 years plus before. So they don't understand that the protons are in the nucleus and the electrons are on the outside. So they made the decision that the flowing charge, because they knew it was a charge flowing in the circuit, the flowing charge would be positive charge. And they made that decision the same way they knew that if you wrote with your left hand, you were possessed by a demon. And that, of course, the earth would be the center of the universe. And that circles were the perfect shape, and therefore all planets should orbit in circles. It was just the way it would be. It's how God would create the things. Only in then the and that also explains why we always use a positive test charge to figure out the direction of an electric field. They assumed it would be positive charge flowing. And so only then in 1910, 1920, when they realized, oh crap, like it can't be positive charge, it has to be negative. They had been using positive charge flowing in a wire for over 100 years. They had been using that to define an electric direction of an electric field too. And so then they were like, well, now what do we do? How do we tell the whole world that we were wrong? So they made the only decision they felt they could at the time. They decided not to tell anyone, and that maybe people wouldn't notice. Well, needless to say, it didn't take that long for people to say, wait a second, if the protons are actually inside the nucleus, how can they be the ones flowing in a circuit? It has to be the electrons. But because of that early decision of not to tell anyone, we still define the electric field as the direction that a positive charge would move when placed in that point in the field. And we will have 2 different types of current that you will encounter depending on what you're learning. You'll hear about conventional current. And conventional current means what's been used traditionally. It's positive charge flowing. You'll also hear about electron current. And it, of course, is negative charge flowing. Now, I use electron current, but your textbook doesn't always. Electricians tend to use conventional current. Physicists, electrical engineers tend to use electron current. So I want you to know I know that both exist depending on where you go in your life so that you'll be ready. In the end, it really doesn't matter. It doesn't make a difference if we think in a circuit that positive charge are leaving the positive end of a battery and flowing in one direction, or if negative charge is leaving the opposite end of the battery and flowing in the opposite direction. In the end, the math is the same and the result is the same because there's two flips and it like one direction and one sign, and so it makes everything work out the same. So I'll always have the current coming out of